let's continue to discuss capacitors. In earlier lecture, we have discussed dielectrics, which is a kind of non-conducting materials. We know the net effect of a dielectric is to reduce the electric field due to the polarization. Now, let's carry out the following experiment to illustrate the effect of a dielectric quantitatively. Here is a parallel plate capacitor with a charge Q0 and a capacitance C0. The region between two plates is free space. The potential difference across the capacitor is delta V0. Noting that no battery in the circuit. This indicates Q0 will keep constant during the process. When we insert a dielectric between the plates, we found that the voltage between the plates decreased to a value of delta V smaller than delta V0. The voltages with and without a dielectric are related by a factor kappa as follows. Delta V equals delta V0 divided by kappa. Because the value of delta V is smaller than that of delta V0, the factor kappa is larger than 1. This dimensionless number kappa is called dielectric constant of the dielectric material. The dielectric constant varies from one material to another. From the definition of the capacitance, we substitute delta V by delta V0 over kappa. The capacitance C with the dielectric equals kappa times C0, considering the charge Q0 on the capacitor keeps constant. Since kappa is larger than 1, C is increased with a dielectric. Thus, the capacitance increases by the factor kappa when the dielectric completely fills the region between the plates. For example, we can express the capacitance of a parallel plate capacitor with a dielectric as this one, C equals kappa epsilon 0A divided by D. Thus, choosing a dielectric with a high kappa is an approach to increase the capacitance of a capacitor. This expression also tells us that the capacitance could be increased by decreasing the separation D. However, in practice, the lowest value of D is limited by the electric discharge that will occur in the dielectric material between the plates. We introduce a quantity called dielectric strength. If the magnitude of the electric field applied exceeds the dielectric strength, a discharge will occur and the insulating properties break down. In such a case, the dielectric begins to conduct. Therefore, the maximum voltage that can be applied without causing a discharge is determined by the dielectric strength of the material for any given separation D. Next, we are going to talk about the equivalent capacitance of a combination of capacitors. Please look at this figure. The left plates of both capacitors are connected to the positive terminal of the battery, and the right plates of both capacitors are connected to the negative terminal of the battery. Two capacitors connected in such a way are called a parallel combination of capacitors. We notice that the potential difference is the same across each capacitor and equal to the voltage of the battery. That is, delta V1 equals delta V2 equals delta V. Let's call the maximum charges on the two capacitors Q1 and Q2. The total charge Q stored by the two capacitors is equal to Q1 plus Q2. That is, the total charge on capacitors connected in parallel is the sum of the charges on the individual capacitors. We then replace Q1 by C1 delta V and Q2 by C2 delta V and have this expression. Now, suppose we replace these two capacitors by a single equivalent capacitor having a capacitance Ceq as shown in the figure. Noting that the effect of the equivalent capacitor on the circuit must be exactly the same as the effect of the combination of the two individual capacitors. That is, the equivalent capacitor must store a total charge Q when it's connected to the battery, and the voltage across the equivalent capacitor is delta V. Therefore, the equivalent capacitor can be given by this one, Ceq equals C1 add C2. If 3 or more capacitors connected in parallel, the equivalent capacitance is the algebraic sum of the individual capacitances and greater than any of the individual capacitances. Please look at this figure. 2 capacitors connected in this way are called a series combination. The left plate of capacitor 1 and the right plate of capacitor 2 are connected to the terminal of a battery respectively. The other 2 plates are connected to each other. Suppose these 2 capacitors are uncharged initially. After connecting to a battery, and the potential difference delta V is then applied across both capacitors. As shown in the figure, the left plate of capacitor 1 is positively charged with a charge plus Q, while the right plate of capacitor 2 is negatively charged with a charge minus Q. Then how about the inner plates? They were initially uncharged. Because the outside plates attract an equal and opposite charge, so the right plate of capacitor 1 will acquire a charge minus Q, and the left plate of capacitor 2 a charge plus Q. As a result, both right plates carry a charge minus Q, and both left plates carries a charge plus Q. The individual voltages across the capacitors are delta V1 and delta V2. Delta V1 equals Q over C1 and delta V2 equals Q over C2. The total voltage across the combination is the sum of the 2 individual potential differences. Similarly, we replace these 2 capacitors in series by a single equivalent capacitor Ceq. Ceq equals Q divided by delta V. Thus, we have this equation. Cancelling the charges on both sides, we obtain the equivalent capacitance for the 2 capacitors in series. When this analysis is applied to 3 or more capacitors connected in series, the equivalent capacitance is calculated by this formula, showing that the inverse of the equivalent capacitance is the algebraic sum of the inverse of the individual capacitance. Therefore, the equivalent capacitance of series connection is always smaller than any individual capacitance. In the last section of this lecture, let's reconsider a parallel plate capacitor. By applying Gauss's law, we have got the value of the electric field E0 in the region between 2 plates. E0 equals sigma over epsilon 0. If we insert a dielectric between 2 plates, as shown in the figure, there is an induced charge QP of opposite sign on the surface due to the polarization. Compared to the induced charge QP, we call Q free charge. So the net charge enclosed by the Gaussian surface is Q minus QP. Now Gauss's law becomes this one. We have known that the effect of the dielectric is to reduce the original field by a factor kappa. Therefore, E equals E0 divided by kappa. From this equation, we could solve for QP, and the relationship between QP and Q is obtained. Substituting QP, Gauss's law with dielectrics could be rewritten as this one, where kappa epsilon 0 is called dielectric permittivity of a dielectric, represented by epsilon. We know epsilon 0 is the permittivity of free space. Kappa is actually the epsilon to epsilon 0 ratio. Here, we define a new quantity electric displacement vector as represented by D, which equals epsilon E or epsilon 0 kappa E. Gauss's law with dielectric could be rewritten as this one. The integral of the electric displacement vector over the Gaussian surface equals the net free charge enclosed by the Gaussian surface. We know a capacitor can also store electric energy. We are going to talk about it next lecture.